Okay, this video is 2A, beginning of chapter 2, and we're going to look at a couple different things. The first major thing we're looking at is the relationship a function? So that's one big key thing here. Second is how to write things in function notation. That's the other big element. And then we're going to look at one piece at the end, and it's called piecewise functions, where one function is made up of pieces of other functions based on a certain domain. And again, we have a lot of vocabulary to go through here, and a lot of these are different ways to determine if a certain relationship is a function. So let's take a look here at some examples. So the first thing we were looking at is the relationship a function? When we talk about a relationship, meaning, for instance, an equation. An equation, all it is really comparing one value with the other value and so forth. So when we talk about relationships, we always have two variables in an equation. Not always, but we like to compare at least two things. So a lot of times we think of it as like XY graph where we have X and Y. But now in this class, we wanted to think about, okay, what is this really? And we always talk about plugging in X to find out Y. Well, we call that input output. You plug in X to get out Y. So the input is the thing that you have control over and that you can plug in. The Y is simply the result of whatever that X is. So we call this function of X, and that's what we're going to be working on here today. Now again, the numbers that you plug in for X, we call that the domain. The numbers that come out as Y is called the range. So those are key terms that we're going to talk to here in the scenario. Okay. Now, for a function to exist, here's the one key element. For every single one input, there's only one output, meaning you can't plug in a value and get out two answers. If that happens, then it's not a function. So notice here, I plug in 4 and I get out an 8 and a 6 at the same time. Can't happen. So we call that not a function. Whereas here, plug in a 4, you get a 10. That's cool. You plug in a 2, you get a 10. So you can have repeated values. That's fine. So it's almost asking like the question, how old are you? You don't give me two answers. You give me one answer. But it's okay to have multiple people with the same age because they're different inputs. So that's kind of how we're looking at it there. Now there's different ways to test this and so forth. One is like a table of values where you list all the x's and you say, okay, here we have repeated input, but notice we have different outputs. So right here it says, this can't happen. This is not a function because, for every one input we have multiple outputs. That can't happen. Another way is called a mapping diagram. So what you do is you list all your inputs over here and you list your outputs over here. So notice this is the same data from the chart above. So notice we had 0, -2 and 0, +2. When you have two lines leaving one input and you get two outputs, it can't happen. So again, this is another way to disprove a function. Now, a big thing is on a graph. How do we show this on a graph? Well, if you graph a function, now here we have, it looks like a parabola on its side, and we'll get to that later in the semester. But notice, we call this thing called the vertical line test. The vertical line, the green line, represents input of x equals +3. So if we plug 3 in for x, what answer do we get out? Now notice on this graph, we get out a +1 and a -1. So you get out two answers. So again, you input 3 and you get out two answers, can't happen. So here's another example of a failed function. So we call this the vertical line test. If you can draw a vertical line anywhere in a graph and it crosses the graph twice, then it fails the function. Now here's another thing we're going to talk about, domain and range. We talked about domain being the possible x values they could plug in, and the range are the possible y values that come out. So looking at this graph, notice the curve goes to the left, and it starts at x equals 4. And it goes to the left. So x equals 3, 2, 1, 0, and all negative numbers. So here we'd say, what are the possible x's that exist on this graph? We would say that x's have to be less than or equal to 4. So that is the domain of the function. Now, the range is, if you plug in those values, what possible y values come out of this? Well, notice as this curve goes up, it goes up, 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 and it goes to infinity to the left, negative, but at the same time, it's climbing up. So if you plugged in negative, 1 trillion, you'd have a y value of like a million, something of that nature. Okay, so we're saying there is no limit on the y values. It goes up forever and it goes down forever. So we call this all real numbers exist. Any output is possible, positive or negative. And the symbol that we use for that is this R with like two lines in it, and that's just the symbol that we use for all real numbers. Okay, so we'll see some examples of domain and range and vertical line test here in a second. Okay, so again, here's some examples, and you can look through these in your notes. But notice we have a vertical line test. I only see one line leaving, so that's good. Here, if I draw in a vertical line, it's only crossing a graph once, so that's good. Now, again, what I want to point out in this example is domain and range. Now here, what x values are possible? So as it goes to the right, it goes forever, and it curves down, but again, it never goes straight up and down. It's always going down and to the right. This side is always going down and to the left. So the domain is all real numbers. Whereas the y values, notice nothing gets higher than this peak of 5. So we'd say the y values have to be less than or equal to 5. So that's what we're talking about right here. Okay, and notice that notation. Okay, so is this a function? Yes, it is. Now, let's talk about the second objective of this video, how to write things in function notation. Now, up to this point in time, we're saying, okay, how do you graph a line? Y equals mx plus b. So you put y is equal to, and the reason why I do that, because that's an output, equals 4 times input minus 3. So when I read this equation, this really reads as the output is equal to 4 times the input minus 3. So a different way of writing this, I'm not changing the equation, it's just a different notations like English and then French. The only difference is a different notation. So instead of writing y, we say the function of x. What is the function output if we input x? Okay, so here we still have this part over here, but instead of putting y, we put f of x. Okay, so we're saying the function gets a result if we input a value for x. And then over here is the actual equation. Okay, so let's take a look here of traditionally how we would do this equation. Okay, so here's function notation. So we say, okay, f of x is equal to this equation. What happens if we plug in -1? Well, you simply write y equals, okay, so because y is your output, and then when you see an x, notice you plug in -1. Okay, so once you do that, you simply simplify and say the y value is 7. So we'd say, okay, if you plug in -1, you get out a 7. Okay, and we would write that as an ordered pair. Now, function notation, we just leave it like this. We say saying f of x, we put f of -1. If we plug -1 in for x, and we can see that here, then the output is 7. So the function of -1 is 7. And as an ordered pair, we see it as a point. Input -1, output 7. Notice this is typically a lot less work, and that's why we do it, because it's an easier way to translate the information, I should say. It's the exact same problem, okay, just a new form, okay? And for, I would say, the majority of the semester, we'll write equations in function notation. And again, this video is just really to try to change your perspective on how do we write this equation. All right. So here's some examples that we see here. You know, is this a function? Yes, because it passes the vertical line test. Notice it's all real numbers left and right, but the range never gets higher than 6 and never lower than -2. So notice the inequality statement that we write right here. Okay, so here's just more examples. I'll have you look through these notes and take a look, and we'll take questions in class on these here. So to go ahead and go through these 4 examples and take a look. Now, the last thing I want to show in this video is piecewise functions. And piecewise functions is, notice, f of x. We're talking about an entire large function, and it's made up of 2 smaller pieces. We have a certain equation that we use, or a certain function we use, when the domain is less than 1 or equal to 1. But if we have a value bigger than 1, we use a different equation. It's very similar to like the post office. If you want to, mail a letter and it's in a standard envelope, you put a stamp on it. It doesn't matter if it's a small letter, a big letter, what the weight is, up to a certain point, it's the same price. But notice once you get to like 2 pounds or whatever the case is, or you use a different size envelope, it jumps to a different equation to calculate the the price of that package. So that's a great example of the piecewise, where the function is how much does it cost to send a package. Well, they have different functions based on different inputs, different size packages. So that's a great application of piecewise functions. So here's more of a mathematical statement here. Okay, so notice in this equation we have one function made up of two pieces. And so let's first look at the top part. Okay, this says when the domain is smaller than 1 or equal to 1. And notice it's a line, 2x minus 1. We have a slope of 2 and with a y-intercept of negative 1. So I draw a line, but notice I stop once I get to 1. And I put a solid circle because it's equal to. But once I get values bigger than 1, then I have a different equation. So this is a slope of 3 starts at positive 1. So if you plug in 1 into the equation, you have 3 times 1 is 3 plus 1 more is 4. So I'm going to start at 4 and then continue to line upward. Okay, and notice they're not connected. So this is like this is the prize that you get if you're under 1 years old, and if you're a toddler over the age of 1, then you get a different price. That's simply what we're saying. We're just translating to a math equation. Okay. So notice here, here's function notation. This is saying if I input 3 into the equation, what happens? Well, first you have to determine, is 3 bigger or less than 1? It's bigger than 1, so I'm going to use this equation, the 3x plus 1. So I'm simply going to plug it in, 3x plus 1. So here's the statement, the function. I plug in 3 for the input, and then I simplify, and 3 comma 10. That's a point on the line. Now notice for this one here, if I plug in negative 1, then I use the other equation because negative 1 is less than 1. And same with over here, number 1 is equal to 1. And so we use the same function, 2x minus 1, 2x minus 1. So notice I plug in the values of negative 1, and you get an output of negative 3 here, and an output of positive 1. So it's all one big function, but we have used different pieces of the function depending on the input. So that's really what we're looking at for here. For class, I would like for you to try this. It's the last blue slide. And we give you a piecewise function, and we give you 3 different inputs. Go ahead and try to graph that if you can. And better yet, plug them in and see if you can get a value. So we'll stop the video with this lesson right here.